I'm John Furter, SMPTE Governor at Large, and I'll be moderating this session. A couple of quick housekeeping things. I'll be holding a stick mic for any questions you may have, and I'll meet you in the middle. If you have a question to ask, please identify yourself, your name, and your corporate or educational institution affiliation so our speakers know to whom they're speaking. Let's get on with it. Our first paper is Search Engine Optimization for Vector-Based Image Search, presented by Jean-Yves Couleaud, Senior Director of Advanced R&D for ADEA. Traditionally, search engine optimization for images relies on keywords either embedded in metadata or placed on hosting pages. Vector-based searches, however, face challenges in adaptively enhancing image discoverability due to the static nature of image vectors. This paper introduces a method to optimize image discoverability for vector-based search engines while minimizing visual impact. Jean-Yves is Senior Director of Advanced R&D at ADEA. His role is to help enrich ADEA's portfolio of media and entertainment IP. His favorite fields include gaming, advertisement, 3D video productions, and computer vision. He built his first convolutional neural network in 1994 and taught it to read books. Before joining ADEA, Jean-Yves was Chief Engineer and Director of Innovation for a large aviation supplier, and helped bring to market one of the first wireless in-flight entertainment systems, and more recently installed the first edge cache on a commercial jet. He holds a Bachelor of Science in Aerospace Engineering and a Master of Science in Signal and Image Processing. Please help me welcome Jean-Yves Couleaud.
Thank you. Mic check? Yes? Okay. We're good. So thank you. Hello, everyone. My name is Jean-Yves Couleaud from ADEA. I'm here to talk about a fascinating subject, a very nifty way to do search engine optimization, short SEO, for image search when the search engine is a vector-based database. I'd like to acknowledge first my colleagues at ADEA, Dr. Ning Zhu, who came up with the initial idea, and other colleague, Matt Adams, who helped me with a simulation. Let's go. Like what's said in the introduction, in traditional search engine, text is king. SEO consists in making sure that you have the right keyword, that your web page has the right hashtag, meta tags, and that your images have the right kind of metadata attached to it. So modern SEO has also some stuff based on backlinks and stuff like that. And so we really need to, but we don't want to talk about that. So when a search engine indexes a page, it looks at elements in the page and generates embeddings that represent the content of the page from a textual description standpoint. So in a sense, if you have a picture of a dog, but your metadata say it's a cat, there's going to be a lot of dogs and cats in this presentation. So yeah, if you have a picture of a dog, but the metadata say it's a cat, and the text surrounding the image is all about cats, then the search engine indexes your image as a cat because it's based solely on text. It does not know what a dog looks like, let alone a cat. Vector search is a little different. Now, vector search is smarter and actually knows what a dog and a cat looks like. And they do so by generating embeddings. Again, we're going to hear a lot about embeddings for both the query, the stuff that you type in the search engine, and the image. And it does compute a proximity, a rank between the two embedding. And if it's close enough that your query and your image have the same type of embedding, the same direction of embedding, then the image is returned. So I search for a dog, I get the image of a dog. If I search for and no cats, they are returned. The trick is really to encode the textual search query in the same space as the image so that both images and text query can be completed. So here we got a little illustration. I stole that from Microsoft, but they're all the same. So you have all data source that transform into embeddings. So that means that if I have an image of a cat, it's going to have a certain embedding. If I have an audio of a cat meowing, maybe that representation is going to be very similar. So some advantage of vector search, it's pretty cool. It is content agnostic. It really doesn't care if you're looking for image, text, video, or other media, that as long as the embeddings for that media were extracted in the same space as the search query. So if you search for cats, again, I like cat, we get all kind of things. I can get like I said, the sound of cat meowing. I can get a French book title that can be translated. Cats are way better than dogs. It does not really require extensive tagging of the new content, as long as you have enough content indexed and recognized. The embeddings have been built, so you don't need to tag your image with anything or really add metadata to your images. So the similarity function also can be easily adjusted. It means that you can actually evolve, get more sensitivity tuning on your search engine. So, but the problem with vector search is that it's not all sunshine and rainbow, of course, because the embeddings are not that easy to compute. And actually, actually they are, but they require a proper model that has been trained to actually compute those embeddings. So once an embedding model is trained, it's hard to change it. It costs a lot of money to train those models. So meaning that once embedding of an image has been computed, there's really no other way to change them than to change the image itself. And that's basically what we're going to do. So tweaking metadata here doesn't really help. Adding keywords don't do anything. You really are stuck with what you have. So, like for example here, if a search engine indexes my wolf here as a dog, there's really not much I can do, because the search engine really thinks that this nice wolf is actually a dog. I told you there was going to be a lot of dogs and cats. So with back to text-based search engine, I don't know how much I have to do. Okay. So my stop is at 1. My stop is when? So I don't know how much I have. Okay. Sorry. So we've back to text-based search. It's pretty easy to actually alter the result. So for example, in my dog here, my huskies. So this first one is a husky. So I would put a tag husky, not Malamute, and this nice dog is a wolf, and definitely not a doggy. And that's how I would let the search engine know that this is a wolf and not a dog. Unfortunately, that doesn't really work in a search vector-based search engine. So, but we really said that vector-based search engine were pretty cool. So to convince ourselves, we built one. We actually built one. It's not that difficult. A lot of people have done it before, so we just adapted for our need. We took CLIP. CLIP stands for Contrastive Language Image Pre-Training. If you've never heard of CLIP, you should check it out. It's almost everywhere now. So it's an AI model that really connects computer vision and natural language processing. It was released by OpenAI in 21, so it's pretty recent but old in this days and time. So in our test, we really input the text query, compare it to the images that we have, and it actually works pretty well. So we think, hey, text vector search probably a good thing, so we should really try to look at how to optimize that. You may have heard of adversarial attacks, sorry. So this one here turned a cat into guacamole. It's a pretty well-known research from 2013. And the idea in adversarial attacks is to create a pattern that you add to an image so that now the search engine, the model, the computer vision model, thinks that it is faced with something else than the original image. So here we managed to turn a tabby into guacamole. So this is really fun. So you may think that, so in the previous one, that study was made with Inception v3, which is an image classifier with 1,000 classes. And you may think, well, that's pretty dumb image classifier. It's easy to fool. What about taking something a little bit more advanced like CLIP? Well, CLIP is also easy to fool. The images are a little crappy, but even with good images, I took that from a research a couple of years ago, I think. And they're still easy to actually confuse the model. So in the first case, you have a deer, and then the research turned it into an airplane. So CLIP is basically the crème de la crème of AI model, and it still gets confused. So let's use that. So in our search engine optimization, we really want to use adversarial attack techniques to enhance certain queries and diminish other queries. So in our case here, this is a husky. I want my image to be returned when I say husky, dogs, or sled dog, but I really don't want that husky to be taken for a Malamute, which is another type of dog, or a pet, and I don't really care about the forest and the trees. So by actually applying modification to the image, we can turn the search engine, the image classifier, in a sense, to think that this dog here is really a husky and not a Malamute. And how we do that? Well, we do an adversarial attack pattern, but instead of just trying to fool the search engine into one unique direction, we actually use multiple directions. And so the multiple directions here are given by the vectors and the embedding vectors that we select to perform the optimization. And so in this particular case, we have a set of intended and a set of unwanted embeddings. The Malamute running dog is the intended one. The husky forest pet tree is the unwanted ones. And so by feeding that into the same model that generates those embeddings, we can actually optimize. But we don't want to optimize like crazy. We still have to keep the image visually relevant. And so that's where we also include in the overall loss computation the perception loss. So really, the only technical slide that is in there, and here is the explanation of what the optimization is. So I can repeat it. We really want to minimize the distance between the vector representation of the optimized image and the intended query vector. And we want to maximize the distance between the stuff we don't want, while at the same time limiting the visual differences between the input of the image. So, the visual difference between the original image and the output images that we generate. And we do that iteratively. And so certain optimization will take us 100 iteration over conversion 10 steps. We're still evaluating why. And so some experimental results. We use Inception v3 on this one, still in image classifier. So we really wanted to prove that we can go into those different directions, not just be the bad guys and turn each dog into guacamole. So in this original image, the dog was classified 84% as a Malamute, 1.7% as a husky. With the optimized image, we just remove any kind of confusion the model could have. It's 99.8% sure that it's a Malamute. And the husky, it's like negligible. And the adversarial pattern, as you can see, we try to visualize it. The colors are not real, but it's a form of visualization. But from just looking at them, they're pretty close. We're in the space of the model, so we are in low resolution. The models is 299 by 299, I think. And so, next example here, it was 79% Malamute, 7% husky. It's not a husky, so let's tell the model. We managed to boost the probability of the models outputting a Malamute to 99.7%, the husky, again, negligible. So I hope you are all dog persons, because there's a lot of dogs. Here, oh, we totally crushed it. We went from 99, the model already thought it was pretty good Malamute, 99.1%, and negligible for the husky, but now it's 99.99%, and the husky is like relegated to history. Let's look at huskies. So this one was interesting. The model thought it was a husky with 28% and an Eskimo dog, whatever Eskimo dog is, 59%. After a modification, here you can see there's a little bit more there was a little bit more work to convince the model to do what we wanted. And so the husky is now 97%, Eskimo dog still 3%, but at least it's not 60% anymore. So I'm a cat person, so I wanted to see if it works for cats. So in this image, you have two elements, and somebody may want that image to only be reported for one of the classes. So for example, here it's a spaniel, 26%. The tabby is completely ignored. The cat is ignored. But in that altered image, we managed to boost the tabby presence by 86%. Well, 86%, and the spaniel disappear as it should. So adversarial pattern visualization, you can see that it's a little bit more pronounced than in the other cases. So I think the further you are from your intended query, the more adversarial you become and the more your pattern will be accentuated. So this image as a story, this is a picture of my cat. So when my wife got this cat, the breeder said that it had bobcat blood, hot bobcat. And so I called that BS, and I had my cat tested for DNA, and there's 0 bobcat trace in this cat. But still, as you can see, Inception V3 thought that it had a 5% probability of being a bobcat. So I wanted to get rid of that. So in this output image, now it's 58% of tabby, and the bobcat has disappeared. So now the truth has won. So conclusion for this study, really we showed that not only we can turn that adversarial approach for the better, and you can actually alter images in a direction that you want an image classifier or an image embedding machine to your intended direction. So what does it mean for a search engine? It means search engines may not always give you access to the embeddings, but there's already tools in insurance search engine to perform SEO. And so our projection is that if a Google or an image library wants to implement a search engine and wants their user to perform search engine optimization, they may give access to certain API that will allow you to actually generate those altered image, those attack patterns that you can add to your image and make them really return for what they're supposed to be returned. Because at the end, it's up to the owner of the image to say what the image is. So even if I publish a wolf, if I want it to be a dog, then I have an opportunity now to make it a dog without modifying the image too much. We have some proposed improvements. We looked at how can we minimize the visual impact. And so if I have already desired query, I have a good baseline for object detection. And so by segmenting image and matching the different objects that the image segmentation process generates, I can actually see what is wanted and what is unwanted. So in our case here, we have we want our desired query to be Malamute dog running dog. So if I feed that to the image segmenter, any segment, something like that, and I see right away where my objects are, and I know by doing semantic analysis how to associate an image segment with unwanted query. So by focusing the alteration in certain areas of the image that you don't want to be returned in the query, you actually keep the integrity of the image in the areas where the query matters. Another thing that we're thinking of that I don't have in the paper here is looking at what happens in the at the resolution of the image. Like I said before, all our tests were done in the space of the image classifier, which was 299 by 299. That's why all my images are square. And so we start looking at how do we scale up the alteration pattern, because the alteration pattern is computed in the resolution of the model. And so that's a limitation that we want to overcome by scaling up that pattern back to the original resolution of the image. So I hope you enjoyed the presentation. Read the paper. There's a little bit more example with a lot of dogs and maybe a little bit more cats. And so if you have questions, now it's the time.
Yeah.
My name is Cooper. I'm a communications student at USC. I was wondering, like, I know a lot of this was cats and dogs, but do you see any potentially maybe like malicious applications of this kind of with like the upcoming election? I'm just thinking in terms of like political media that could be put out there. Do you see any way that this could be used for ulterior motives? Yeah.
Well, the origin of this method is for nefarious purposes, right? So of course it can be used for that. One of the very bad use case that I am aware of is confusing cameras in cars, in self-driving cars, so that they don't really understand what a sign is. So you can turn a stop sign into a speed limit sign by just putting, it's actually real. You don't, you act in real life by sticking stuff on the, putting stickers on a roadside. So that confuses the hell out of the AI in the cars. Same thing with face recognition. You can actually put a t-shirt that has some weird patterns that also confuse the facial analysis, because facial recognition starts with facial detection. If you defeat the detection phase, then the recognition phase is defeated as well. So yes, there are obviously stuff. In our case, we can even go further, because we can drive it into a accentuated direction and minimize another direction. So when you have I don't know, an image that has no inherent political meaning, for example, you can actually say that shows that this thing happens. So yeah, obviously this had to. Yeah.
Robert Harker, and I'm the oldest SMPTE student member. I go to City College San Francisco. And my question, I hope it's not a newbie question, but could you do a brief introduction of what vectorization of an image, how it works?
Yeah. So vectorization is basically a reduction in dimension. So an image is a collection of pixels, right? And there's not an infinite, but there's a huge combination of pixels. Each pixel has, I don't know, 255 by 255 by 255 value. So in order to be able to manage those images, you need to move into a space that's manageable. And so that's, Clip, for example, turns any image into a vector of 512 components. And each component is an integer. I'm not sure about so even if the image is 10,000 by 10,000, at the end it becomes a 512 component vector. So once you've done that and you've done rules, you've set up rules to how those pixels are turned into that vector, then you can start making comparisons. And so the machine learning model that generates those embeddings understands the image and spit out an embedding. And so, for example, in the image classifier, it's 1,000 classes, and you have a value for each of those classes. And so that vector of 1,000 can be compared to another vector of 1,000. So, for example, if I have in the classifier here, the spaniel, there's a component that means spaniel. And it means only spaniel. And if that component is here, that means that the model thinks that there's a spaniel in the image. And so that's the vector is that 1,000 different data value that we have. We can talk later if you want. Because I think we're running out of time, aren't we? No? Well, one more.
So the vectorization is built on top of object recognition?
I'm sorry?
The vectorization is built on top of object recognition?
Kind of.
So you do object recognition.
Well, you don't. It's a one big thing. Clip is, for example, clip. You just feed it an image and it spit out a vector. You feed it a text and it spit out a vector. And those two vectors are in the same space. So you can compare. So you can compare image with text. That's probably because I'm not a teacher.